Kevin Sepchik. I'm a control systems programmer here at ARC Specialties. I'll be talking about different kinds of robots and what makes different robots different, some of their strengths and weaknesses, and what makes them good at different things. The most important difference between different robots is the degrees of freedom. Some of the other differences are the workspace and footprint of the robot, the precision or accuracy of the robot, the payload capabilities, the speed, and the stiffness of the robot. Degrees of freedom is the different ways a robot can move. Some of this is based on just the number of axes or motors that the robot has. Some of it is based on the way those axes are arranged. So one thing that we can talk about is the positional degrees of freedom. That's the different ways a robot can move an object. You've got translational degrees of freedom, forwards, backwards, side to side, up and down. And then you've got rotational degrees of freedom, roll, pitch, and yaw. There's always 6 degrees of freedom. No robot can have more than 6 degrees of freedom for any one particular thing that it's positioning. And it can't have more degrees of freedom than it has axes. But some robots will have extra axes that give you redundant degrees of freedom. So workspace is another important thing on the robot, and it's basically what you think it is. It's the area that a robot can work in. Footprint is the area that it takes up while it's just sitting there waiting to do some work. Precision is the repeatability of the robot. It's the smallest move that a robot can consistently make. So if you need to split a hair, then you need a very precise robot to always go to the middle of the hair. Accuracy is how good the robot is at locating things in space. So if you need to drill 2 holes that are exactly a foot apart, give or take a hair, then you need a very accurate robot. The last 3 characteristics of a robot are speed, which is exactly what you think it would be, how fast a robot moves. Payload, which is the heaviest force the robot can exert. Usually we call it payload because mostly robots are picking things up and moving things around. But it's also, if you have a machining robot, it's the amount of tool force and tool load that the robot can apply to a tool. And then stiffness is like spring stiffness. It's how much the robot is going to move from where it wants to be when a load is applied to it. So how much the robot droops when you're picking up a heavy part. So on to the different types of robot. One of the simplest types of robot is a Cartesian robot. It's a robot that has some number of linear axes, straight line motion axes. These robots are anything from an automated gantry crane to something like the nice little 2D degree of freedom elevator that's in soda machines. Cartesian robots have the largest range of capabilities. You can have very, very precise and accurate robots for doing things like machining mirrors or measuring things, or you can have very large, inaccurate robots like a gantry crane. One of the only things that's the same across all Cartesian robots is that the footprint is always as big or a little bit bigger than the workspace of the robot. You can't really have a Cartesian robot that works outside of its linear rails and linear axes. So it's always going to be working inside of that space. The next kind of robot is going to be a Scara robot. That's like a step up in complication from a Cartesian robot. It has 2 rotational axes and then a linear axis. So Scara is selective compliance articulated robot arm. And it's articulated because it has those rotational axes. So it'll have 2 axes that move kind of like your arm if you're keeping it on a flat plane. And then it has a vertical axis that'll move things up and down, and sometimes a rotational axis to rotate the tool after that. It was inventive to get that compliance for working with inaccurate holes. So the rotational axes have some compliance, they have some bendiness. So if you're trying to locate something in a hole that's inaccurately located, having a robot that'll move a little bit while it's locating the hole is useful. They're generally faster than a similar Cartesian robot because they're only moving that arm around, not a gigantic rail. They'll usually have less payload capabilities just because they're generally smaller. Building a large Scara robot is pretty complicated because you have a very large cantilevered load there. But they do have a much smaller footprint for their workspace because they have that arm that's reaching out from a central base. So they can take up less room than a Cartesian robot. They're usually used for small assembly tasks or pick and place operations. So a step up from the SCARA robot is the articulated arm robot. This is what you would think of as a standard industrial robot. It's the kind of robot that you'll see Tony Stark working with in Iron Man. Usually has 6 axes in it, so it'll have 6 degrees of freedom. It can move X, Y, and Z, and it can rotate in whatever direction you want it to. These have the same workspace advantages as the SCARA robot because they're an arm reaching out from a central base. So the workspace is bigger than the footprint that it takes up. They're somewhat less accurate because as you have all those rotational axes, small machining errors will stack up and generally make the accuracy lower because it's a small error at the base of the robot magnifies to a large error at the end of the robot. It can be calibrated to take care of some of these issues, but it's still generally going to be less accurate than a Cartesian robot. The advantages of articulated arm robots are that because they're so common, they're made in a large range of sizes. So you'll have anything from a desktop-sized robot up to a 1-ton robot that can move cars around. A completely different kind of robot is a delta robot. It's called a delta robot because it has 3 legs and a triangle that are all attached to a platform. By moving the legs around, you can move the platform around. So all of the motors are up at the top, and the only thing that you're moving is this very lightweight platform down at the bottom. Because the arms are lightweight and the platform is lightweight, delta robots can move extremely quickly. And they're very stiff because they have all 3 legs holding that platform. So they're very fast, they're very precise, but they have very low payloads because the motors are all the way up the top and you have a very high leverage, so very low payload. They're useful for doing pick and place operations. You'll see them in pharmaceutical companies or electronics companies where you need to assemble a board with a bunch of chips on it very, very quickly. So they'll very quickly pick up the chips and put them in place from all different locations. They're very fast, they're very good at that. The downside is that they take up much more space than they can actually reach and work in. You have the whole base at the top with the legs reaching down, and then a very small workspace underneath for them to reach and work in. So they're good at fast assembly tasks, but they do take up a lot of space. So industrial robots are usually kept in cages and enclosures because it's very likely that they'll injure someone who wanders near them while they're operating. A new kind of robot that is just being developed in the last decade or so is a collaborative robot. These robots are mechanically designed with less stiff axes, so they're more compliant, less stiff. And then they have control algorithms that will limit the force, the speed, the momentum, all the things that are dangerous about normal industrial robots. So with a collaborative robot, you can set it up so that it's safe for a person to work around.